Bismillahirrahmanirrahim. Dear students, today we are going to discuss a new series of reactions which belong to the carbon oxygen bond formation. The first reaction today we are going to discuss from this series is Keck Macrolactonization. This reaction is basically about the formation of ester linkage, cyclic ester, from carboxylic acids which also bear hydroxy group. That is, the substrate is hydroxycarboxylic acid, which is converted into ester linkage by interlinking these two functionalities, that is carboxylic acid and hydroxy functionality within the same molecule, and so we get a cyclic ring type structure having ester linkage, and these compounds are known as lactones. And so macrolactonization means this cyclic ring can be 6 membered, 7 membered, 8 or more number of carbon atoms can be in the cyclic ring. So therefore it is also termed as macrolactone, and the process macrolactonization, and this process was the introduction by the Keck scientist, and so we name this reaction as Keck Macrolactonization reaction. This reaction has been divided into two parts. Today's lecture is about the introduction to macrolactones, and then introduction to Keck macrolactonization process, the reagent used for this reaction, the way of mechanism, way of the addition of these reagents for the formation of the macrolactones, and then discussion or introduction to some different macrolactonization reactions, which are also, these reactions are also used for the process of macrolactonization along with Keck macrolactonization in the synthesis of natural products. And in the end we shall discuss the overall mechanism of this Keck macrolactonization. The mechanism is further divided into three categories. That means we are going to discuss different types of mechanisms for the same reaction. So all of these will be discussed in detail here, inshallah. Here is some general introduction to macrolactones. First, the lactone is the class of compounds which are generally known as cyclic carboxylic esters. These are formed through intramolecular esterification of hydroxycarboxylic acid. Intramolecular term is familiar to you. We know that the opposite of is intermolecular. Intermolecular means two different molecules are interacting with each other and making a joining bond. But intramolecular is the reaction in which the two moieties within the same molecule, same species, are interacting with each other, and as a result of intramolecular reaction or interaction we get a cyclic structure. So intramolecular esterification between carboxylic acid and the hydroxy, that is alcohol, within the same moiety result into the formation of a cyclic ester. If the chain is so much long that after cyclization we are going to be obtained by 5 or 6 membered ring, then this process occurs simultaneously. That is, the formation of 5 membered or 6 membered lactone is spontaneous and easily progress reaction. But the formation of 3 or 4 membered rings or cyclic lactone is somehow tough, and also due to ring certain they are found to be very reactive, and their isolation is too much difficult due to less stability and high reactivity. These 3 or 4 membered rings are also termed as alpha lactones and beta lactones. We will explain this nomenclature also. The different nomenclatures are used for the naming these electrons. First type of nomenclature is about the use of the acid from which this electron is going to be formed. The name of acid followed by the suffix electron. For example, if we are using acetic acid, then this term is named aceto for 2 carbon atoms in the chain. If 2 carbon atoms are in the electron, it means it will be 4-membered ring. 2 carbon atoms, 1 for oxygen of ester and 1 for carbonyl of ester, carbonyl carbon of ester. So there will be 4-membered cyclic electron if 2 carbon are present, and we name it acetoelectron. If 3 carbon are present, that is the ring will be 5-membered. 3 carbon and 2 are oxygen and carbonyl carbon, and so this these 5-membered ring will be termed as electron will be named as propiolectron. Similarly, for 4-membered carbons, 4 number of carbons are 6-membered ring, we will term it butyrolectron. For 5 number of carbon atoms are 7-membered ring, we will name it valerolectron. Valeric acid, 5-membered 5 carbon acid is known as valeric acid. 6 number of carbon atoms acid is known as caproic acid, from that caprolectron, having the cyclic ring will be 8-membered ring. First way to name an electron we have discussed, which uses the name of the acid from which the electron has been derived. The second way for the naming electron is the use of the Greek word letters like alpha, beta, gamma, etc. These letters are used in such a way that it depends upon the size of the electron ring. That is, alpha electron is used for a 3-membered ring. 3-membered ring mean 1 carbon is involved only there, and the 2 member of this 3-membered ring are oxygen and the carbon of carbonyl group. That is, in addition to ester, two member of from ester linkage, 1 carbon and 1 oxygen, we have only 1 carbon. That is termed as alpha electron. And in case of beta electron, we have 2 carbons here in addition to the ester functionality, so overall the ring is 4-membered. Likewise, for gamma electron there is 5-membered ring because it involves 3 carbons in addition to 2 member from ester linkage. So the second way of naming these electrons is alpha, beta, gamma and so on, but as we know, this is too tough to use this Greek letters for large number of rings. So this letter naming by these letters is suitable for small membered alpha, beta, gamma, delta, theta, psi, phi and so on, but for large number of member it seems to be too tough. The next term which is basically involved in our lecture, which is macroelectron. The macrocyclic electrons are known as macroelectron. We have discussed here 2 types of nomenclature for naming electrons. For macroelectrons, mostly there is used general name which are involved in the natural product chemistry. Here you can see the example. The suffix the used for the electron is olide, and we use this the term olide as a suffix at the end of the general name of that species. For example, here you can see the 4 different types: butenolide, macrolide, cardinolide, or bufadienolide. Here you can see the structures of these moieties also. Butane mean 4 carbons. Here you can see the 5-membered ring in which 4 carbons are involved, 1 of ester linkage and 3 are other carbons. And butene, because 1 double bond is there, therefore it is termed as butene Olide is the suffix for lactone. So overall this moiety is termed as butenolide. Butenolide is a general term which is also involved in a large number of molecules which are produced due to substitution on this moiety. And basically this butenolide is in general form, or in the term of heterocyclic chemistry we name it 2-furanone. We know that furan is the cyclic 5-membered ring, and here at second position there is ketone functionality, carbonyl functionality, so we are naming is 2-furanone in the chemistry of heterocyclic. But in general chemistry we name this it as butenolide. Second was the macrolide. Macrolide is a general class which involve large number of cycles in organic chemistry or natural product chemistry. Here the one of the macrolide is shown here, which is named as erythromycin, and here you can read the structure of this erythromycin and the microcyclic ring. Two glucosidic glucose type cyclic glucose type linkages are shown, or moieties are shown here, and the other part of the molecule is a cyclic ring which bear an ester linkage. You can see on the left side of the molecule at the bottom there is ester linkage, and this ester linkage is involved in a large number of cyclic ring which is involving I think 2, 4, 6, 8, 10, 12, 14 number of carbon 14 membered ring. The third example is cardinolide. Cardinolide is you can see at the top of this molecule structure there is butenolide, which is further substituted by a steroid moiety, and so this term is now named as cardinolide. And similarly the bufadienolide is also involving the steroid type structure which is substituted on a 6-membered cyclic ring which is bearing 2 double bond. So therefore in the structure in the name we are also using diene for 2 double bond, and this overall this molecule is named as bufadienolide for this lactone structure. Keck Macrolactonization was introduced by Keck and Boden in 1985. Before their invention, their discovery, in mid of 1970s, Core-Nicolau macrolactonization process was a tremendous invention or discovery for the total synthesis of the natural products, because a large number of natural products involve the lactone moiety. So but that we shall discuss on next slides also about this reaction, how it is performed, but to involve some simplicity in this reaction in this process of macrolactonization, in 1985 Keck and Boden tried to develop a macrolactonization protocol which involves the activated ester. First step of this macrolactonization is the creation or generation of activated ester, which has been created for the progress of the reaction from hydroxy carboxylic acids. But this they try to generate this activated ester from hydroxy acid substrate with in situ generation, and without purifying or without isolating it, they want to move towards the product, that is the lactone formation. You know the term in situ mean the creation of the generation of a species, a molecule in the reaction mixture. That is the thing is the species created in the reaction mixture, and then it is moved toward the further steps. So the Keck and Boden tried to use the esterification reaction or mechanism or method given by Steglich esterification method, which uses DMAP and DCC. We shall show the structures of these moieties also on the next slide. these moieties are involved in the formation of macrolactones, and but by using these two, only these two functionalities, these two molecules, that is dimethylaminopiridine DMAP and dicyclocarboimidine DCC, they found that there was no progress of the reaction towards the product side, that is the formation of lactone, by using these two moieties. Here is the general reaction shown for this Steglich esterification, which involves the reaction of a carboxylic acid and an alcohol in the presence of DCC and DMAP. With the removal of water, we get the ester linkage. This is the basic Steglich esterification reaction. So due to non-formation of the product, that is lactone, by using this Steglich esterification, Keck and Boden decided to modify something in this reaction condition to get the required product. So the basic Steglich esterification reaction was unable to get the lactone or macrocyclization process. So Keck and Boden modified this by using a proton source like HCl, and they uses HCl salt of dimethylaminopiridine. And due to this involvement of this protonated or salt form of dimethylaminopiridine, the result was good, and they obtained macrocyclization or macrocyclized products in good yields. So the formation of medium and large size lactones from hydroxy acids by using dialkyl carbodiimide. Dialkyl means this can be dicyclo, as we have mentioned on the last slide, that is DCC. Dicyclocarbodiimide or can be substituted by some other alkyl moiety also, and an amine hydrogen chloride, which was basically used dimethylaminopiridine as a base in its salt form with HCl, and an amine base also, that was also DMAP only. And so this the cyclization process in the presence of these reagents is generally known as Keck Macrolactonization process. Here is the general reaction shown for the Keck Macrolactonization. As you can see, the hydroxy acid, N stands for the different number of carbon atoms, which may result into large cyclic lactones. In the presence of DCC, DMAP, HCl and chloroform as a solvent, and we get the formation of lactone. Here another way to see this reaction is here by using N, and here you can see the N is greater than 1. N can be 1 because we can get the 6-membered ring also by this Keck macrolactonization, but generally this reaction is used for the large number of rings, for the generation of large number rings. So due to generation of large number of rings, this term as macrolactonization, and so in that case N, the value of N will be much more greater than 1. Here is some more general explanation of the Keck macrolactonization reaction. First, in 1985, Keck and Boden were to introduce a cyclic lactone, and they cyclized the 15-hydroxy pentadecanoic acid, that is 15 number of carbon atoms was present in this hydroxy carboxylic acid. And then in the presence of DCC, using 3 equivalent, that is 3 equivalent mean if we are using this hydroxy carboxylic acid 1 mole, then DCC should be 3 mole, DMAP should be 3 mole, DMAP HCl should be 2 mole, and chloroform will be used as a solvent. Under refluxing of 16 hours, we get the product cyclized lactone up to 95% yield. And the general representation of Keck macrolactonization can be shown as the hydroxy acids in the presence of DCC. DCC can be greater or equal to 1 equivalent, or EDCl can also be used here. In place of DCC we can use EDCl, which can be also greater than 1 or equal to 1 equivalent. DMAP greater than 1 or equivalent to 1 equal to 1 equivalent. DMAP HCl also greater than 1 or equal to 1 equivalent. Because this depends upon the nature of the substrate, some require some tough conditions, so in that case we have to use some regions in high concentration, and in some cases we have our product is achieved in low concentration also. Solvent is used and reflux is required for the progress of this reaction, and slow syringe pump addition of substrate. Substrate is added previously going on reaction in the form of syringe pump, that is, it is added in very small amount over a large time, that is drop wise. It is added drop wise. Then we get this cyclic ester, state chain ester, and this is known as activated ester, which after the loss of thiourea product, substituted urea product, we get the medium or large ring electron. The different regions, different regions used in this reaction are shown here. First is here EDC or EDAC or EDCl, that is 1-ethyl 3-dimethyl amino propyl carbodiimide. If you see the nomenclature of this carbodiimide, because here you can see the C double bond N is imide and there are 2 C double bond N, so it is termed as carbodiimide. And if one carbon is numbered 1, one nitrogen is numbered 1 of this carbodiimide, then the other nitrogen will be number 3. Now number 1 is termed for ethyl, which is attached to the nitrogen, is this nitrogen is termed as 1, so we are naming it 1-ethyl, and the other nitrogen of this carbodiimide is termed as 3, and at this 3 there are the substituent present is 3-dimethyl amino propyl. Here you can see at nitrogen there is propyl 3-membered ring, and which is further attached to amino, and amino is attached to 2-methyl, so this substituent will be termed as dimethyl amino, and dimethyl amino is present at the third position of this propyl, because this propyl is attached to nitrogen at one position and at the third position is dimethyl amino, so we are naming it 3-dimethyl amino propyl moiety, and it is attached at 3 position, so overall name is 1-ethyl, and first 3 is for the nitrogen and the second 3 is for the propyl group. So 3-dimethyl amino propyl carbodiimide, and the different here you can see in the second structure there was EDCl only written, which can be used in place of DCC, but EDCl, in addition to EDCl, this compound can be abbreviated in the form of EDAC or EDC. Next is the in place of this EDCl we can also use DCC, that was the first used by the Keck and Borden for the macrolactonization process. This molecule is termed as N-prime dicyclohexyl carbodiimide. In place of N-prime we can use also 1,3 dicyclo also. Similarly, in the first compound, that is EDCl, we termed 1 and 3, that can also be termed as N, and in place of 1 there should be N, and in place of 3 there can be N prime also. So this molecule N-prime dicyclohexyl carbodiimide or 1,3 dicyclohexyl carbodiimide, abbreviated as DCC or DCCD. And the third moiety which was used in this reaction is 4-dimethyl amino pyridine, DMAP. Here you can see the 4 for the fourth position of pyridine ring, in pyridine heterocyclic ring, nitrogen of this heterocyclic ring is termed as 1, and then the at fourth position the group dimethyl amino is present, so this compound is termed as 4-dimethylamino-pyridine, DMAP. If you talk about the DMAP HCl structure, what is do you think about the formation of the salt form of this? There are two lone pairs in this DMAP. If we add HCl to this two, then which nitrogen will be protonated and which nitrogen will not be protonated? If you keenly see, then you will easily come to this point that the nitrogen or a lone pair of dimethyl amino group can resonate into the ring, but in case of pyridine, the nitrogen lone pair of nitrogen never resonate into the ring, and it is available for the protonation. And you know, we use pyridine as base in many organic reactions or in the synthesis of complexes. It is used as a pyridine as a base or ligand also. So the among these both lone pair, the lone pair of nitrogen of this pyridine ring will be involved in protonation, and the HCl will be attached with this nitrogen instead of the nitrogen of dimethyl amino group. Here is given some introduction to the related macrolactonization reactions. First is the Corey-Nicolau macrolactonization reaction. Both of these scientists used hydroxy carboxylic acid as a substrate, but they converted into a lactone by using 2,2-dipyridyl disulfide. Here you can see the structure of this functionality. Pyridine 2 pyridine ring at second position are attached to a disulfide, though 2 sulfur, and so it is termed as 2,2-dipyridyl disulfide. In the presence of triphenylphosphine as a base, which is added as 1.5 equivalents, and by using solvent, the reaction is taking place at room temperature and takes a time of 5 hours. And here n is shown to be greater or equal to 3. Here you can see the formation of 2-pyridinethiol ester. This ester is separated and isolated. Then in the second step, this is added into the solvent with high dilution, then refluxed for 10 to 30 hours, and we get the formation of lactone here. So this reaction takes place in 2 steps, but the Keck macrolactonization was going on in 1 step. That is, there was no isolation before the product formation. Second relating macrolactonization reaction is Yamaguchi macrolactonization reaction. This reaction also uses hydroxy carboxylic acid, but it uses the other reagent 2,4,6-trichlorobenzoyl chloride in 1.1 equivalents, and the base used for this is trialkylamine, that can be triethylamine generally, and which is added 1.1 equivalents. THF tetrahydrofuran is a solvent, room temperature is required, and 2-hour stirring. Also the salt of trialkylamine is added here, and we can filter off the product of mixed anhydride, and then mixed anhydride is added to the solvent with high dilution along with DMAP, dimethylamino-pyridine. The slow addition via syringe pump reflex. Through syringe there is slow addition of the reagents, and we get the cyclized product of lactone. So both of these discussed reaction here involve 2 steps for the formation of lactone, but Keck macrolactonization is showing preference here because of one pot synthesis or single step formation. The third most relating macrolactonization reaction is Shina macrolactonization reaction, which proceeds in 2 different ways. One way, by using Lewis acid catalyst, and second is by using nucleophilic catalyst. By using Lewis acid, in both of types you can see omega hydroxy carboxylic acid is used, which is also known as seco acid, and used through slow addition of this substrate. And this is treated in using Lewis acid catalyst. It is treated with trifluorobenzoic anhydride, and acid catalyst is used. Lewis acid catalyst is used here, like aluminum chloride, etc. We know that Lewis acid is the acid which can accept a lone pair of electron. A pair of electron is termed as Lewis acid, and the donating species is termed as Lewis base. 50 degree C temperature is required in case of Lewis acid, and we get 88% yield of this thibitolite lactone, which is a synthetic musk. If we use the nucleophilic catalyst, then this omega hydroxy carboxylic acid is treated with methyl nitrobenzoic anhydride. The catalyst is nucleophile, and amine is trialkyl amine. Room temperature is required for this reaction, and we are getting the product with 95% yield. That is, thibitolite with 95% yield has been prepared through this method of using nucleophilic catalyst, but by using Lewis acid catalyst 88% yield was obtained. So this is the overall introduction of some different macrolactonization reactions which are relating to this process of Keck macrolactonization process. The mechanism of this Keck macrolactonization has been categorized into three different categories. First category of mechanism is shown here, that which involves the first step of formation of the activated ester intermediate. This first step does not mean that it is isolated and then in the second step the other agent is added. These steps are named only for this mechanism sort. In practical, it is one step reaction. The first hydroxy carboxylic acid is treated with the DCC or carbodiimide category. Here you can see the two nitrogens of imide bearing lone pair can act as a nucleophile, and the carboxylic acid can act as a protonating agent, and it protonates this moiety, and we get the imide, protonated imide, diimide, and then the anion produced by this carboxylate attacks as a nucleophile on the carbon of diimide, and the double bond of protonated nitrogen is converted into single bond, and we get an activated ester. Activated ester because here you can see the formation of ester linkage here, but this oxygen is attached with the carbon, which is further attached with the sp3 hybridized nitrogen and also with the sp2 hybridized nitrogen. So therefore this ester is termed as activated ester. The difference, all of the three mechanisms are similar, show similarity at this step almost, but the difference starts from here. In this mechanism you can see the activated ester is getting the proton from dimethylaminopyridine HCl. Here you can see the structure of DMAP HCl which is given with the dimethylamino nitrogen. That is protonation has been given, proton has been given to the dimethylamino group, which is not correct. But this mechanism, to show this mechanism I was to discuss this, but this structure is not going to be correct one. Okay, the proton is given to this oxygen of ester linkage, and after shifting this proton to this oxygen we get the this oxygen in the protonated form, and also the chloride HCl which was present with the protonated DMAP is now present with this positively charged oxygen to balance it, and we are getting the byproduct of DMAP. In the next step again DMAP comes and it removes along with the HCl and we get the cyclized product. This cyclization you can see here, the lone pair of hydroxy group attacks on the protonated ester linkage and the carbon oxygen double bond moves towards the oxygen, which is becomes OH, and a chlorine moves this hydrogen in the form of HCl, and we get again double bond. But in this regaining of this double bond, the substituent of from the imide moiety is removing in the form of a urea product, and here you can see the formation of lactone here. The second mechanism is used starting from DCC, dicyclocarbodiamide, which is first protonated, and after protonation it interacting with the hydroxy carboxylic acid, and similarly oxygen of the carboxylic acid attacks on the carbon of electrophilic carbon of this carbodiamide, and protonated nitrogen gets the single bond, or its positive charge has been removed, and we get the product here. And in ester formation, which is termed as activated ester, and in the second you can see the attack of the pyridine from dimethylamino-pyridine from lone pair of nitrogen of pyridine on the carbonyl carbon of ester linkage, and oxygen gets the negative charge. Then this negative charge comes back, and here in this case you can see this oxygen gets the negative charge, which is protonated, and it becomes OH, and in the next term after deprotonation the carbon oxygen bond gets the double bond, and the carbon oxygen of the imide C double bond N functionality moves towards is broken, and the carbon oxygen bond single bond gets double bond, carbon nitrogen double bond is has become single, and nitrogen is protonated. And we get here the next functionality or molecule here, in which now the carbonyl functionality is attached with the dimethylamino-pyridine functionality. In the next case step, the hydroxy of lone pair of hydroxy group attacks on the carbonyl, and carbon oxygen bond becomes single, and then it is protonated, and when this protonation proton is removed, oxygen gets the double bond, and nitrogen pyridine bond has been broken, and we get removed by the neutral DMAP along with the formation of lactone. And in the last step we were obtained, or we were given the side product of urea, cyclosubstituted urea product. Here is the last one, third mechanism. Here you can see the first step, which was similar to the mechanism number 1, that is proton from acid is obtained by the DCC, and it after protonation the O minus attacks on it, and it is on the carbon, and the double bond becomes single bond, we get the activated ester. In the second step now DMAP HCl comes and attacks on this activated ester. Here you can see the proton of this DMAP is obtained by the N double bond, sp2 hybridized nitrogen of this activated ester. This activated ester contains two nitrogen, one is carbon double bond nitrogen, that is sp2 hybridized nitrogen, and the other is carbon single bond nitrogen, which is sp3 hybridized. The sp2 hybridized nitrogen gets the proton from the protonated DMAP, and it is protonated. On the same time the lone pair of dimethylamino group moves towards the benzene ring, making the lone pair of pyridine more activated, and it attacks on the carbonyl carbon of the ester linkage, and at the same time carbon oxygen ester bond has broken, and it moves towards the imine moiety, where carbon oxygen gets the double bond and carbon nitrogen double bond becomes single, and we are removed with the formation of urea byproduct. and the second main product was now the attachment of this dimethylaminopyridine functionality with the carbonyl. In the next step, the lone pair of hydroxy group attacks on the carbonyl carbon of ester linkage. Oxygen gets the negative charge, and when this negative charge comes back, the carbon nitrogen bond is broken, and all the bonds moves to their original position, and we are removed with the dimethylaminopyridine neutral functionality and along with the formation of lactone. So this is the third type of mechanism which has slight difference from the previous mechanism. So these three different types of mechanisms have been discussed for the comparison of the formation of these this final lactone. If you ask the question which mechanism is the correct one, 1, 2 or 3, basically in deciding mechanism we have only the intermediate, or sometimes we have isolated intermediates that compel us, that show or indicate us some pathway of the reaction. But in some cases we do not know about the intermediates in normal conditions. But for the study of the kinetics or study of the mechanism, there are involved certain techniques which slow down the reaction pathway, reaction mechanism, and we easily can interact or isolate or found the presence of different moieties in the reaction mixture, and this thing gave us hints some about the pathway of the reaction. So all of these reactions, to compare all of these reactions, the main functionalities or main products are similar. The main intermediate which was expected is just similar, but the formation of the pathway is different, because all of these things are present in the reaction mixture, and these things can happen in one way or some other way. So there are possibilities for the reaction pathway from the one way or from the other way, because the interacting species, the region used for this species are present there. So they are not going to involve some species which are not present in the reaction mixture, or some species which are totally impossible according to the chemistry of the reactions. So all of these things can happen in the reaction, and these all of the three mechanisms can be right or can be correct.